Mark P. Otten back with you.
Okay, this is your structural equation modeling estimation PowerPoint summary. There is a little bit of background noise here and there as I'm filming this during my lunch hour in my office, and sometimes there's noise outside during the lunch hour. But anyway, we will power through. You may not notice at all, so if not, never mind. Okay, so the first thing that I want to tell you about model estimation for SEM is that the first time that I saw this personally, I was overwhelmed, and I had that reaction that I have described to some of you guys in the past, where, at least I think I have, where you see an equation or a set of numbers or a mysterious-looking thing within a research paper or in a textbook, and you just sort of blank out and you're like, I have no idea what's going on, and there's no chance that I'm going to understand this right now. And then you come back to it later and you're like, I kind of want to just skip past this and get to the answer and not understand it. And like the first time I studied SEM, I did that for this model estimation stuff for the most part. and it was tough for me to actually go in and look at it and try to figure out what was going on. But once I did, I started to think that SEM was even cooler than I realized. But this is still just, and it's because there's a lot that goes into these conversions of our statements of equations and Bentler-Weeks model, matrices. There's a lot that goes into converting those from statements to then equations with numbers in them and ultimately solutions for to match to your hypothesis. So when we see, so like in this video, we're going to see some of that, but we're not actually going to see all the details. I'm not going to work out matrix algebra in this lesson, so there will still be a black box of mystery that you will be left with probably, and some of you guys will be like, I'm okay with that, I don't really care. And then others of you will be like, that's interesting, I want to go into that more. And then if you're that second person, feel free definitely to come talk to me. There actually is not an in-depth explanation of this whole thing, even in the chapter that Jody Ullman wrote in the Tabachnik and Fidel book, because that's kind of a summary in itself of all of this stuff. So there's enough in there to get you through an example, but there's not enough in there to explain all of the decisions that SEM researchers have made over the years to go with this instead of that, or what's the background as far as why were these equations were selected versus others. So there's plenty to wonder about still as we go through, and I will try to navigate that with you as best I can, given that this is going to be a relatively quick introduction to get you to the point where you can run something in R, get your answer, and then interpret a little bit better than you would have if you hadn't seen this stuff. So that's what we'll try to do. We'll base it on the Tabachnik and Fidel or the Jody Ullman skiing example again. I don't want to get tired of this example, but this is small enough and clear enough, I think, in its presentation that we can proceed with some knowledge of what exists in there, which will then inform, it already did inform our Bentler-Weeks model that we represented this model with, and then we can translate this, since it's familiar, hopefully, to how these star values, how these statistics come out of such a model. So we've said in general, our first step is to plug in start values, and that the computer program does that for us. So these are guesses based generally on the idea that if you have a predicted relationship in your model, such as love of skiing predicting ski strip satisfaction, we've specified that as a predicted relationship. So then that value is going to go in as a start value that's higher than 0. Higher also than the relationships that do not exist in our data set. For example, sensation seeking and love of skiing, unrelated in this hypothesis set, so that start value would be lower, or 0. But again, we don't make those decisions ourselves because the computer program will do it for us, and the worse the computer program does, like the further off the start values are, that's fine. It's just that the solution will iterate, take longer basically to iterate to get to a final solution, but it'll still get there. So we rely on the computer to do this. And then it says we calculate. The computer will calculate estimated covariance matrices based on our model. This is your model covariance matrix that then ultimately gets compared to your data covariance matrix. And like I mentioned, this solution is iterated. So I'm going to expand on that just a little bit more here. Maximum likelihood estimation is going to come into the picture in this iteration process. You guys may have heard of maximum likelihood estimation in studying exploratory factor analysis in the past. If you've never seen maximum likelihood estimation before, that's okay. We'll just kind of take you through this example and explain a little bit what it is as needed. But it's going to drive our iteration process of this covariance matrix. So this is a slide that I've shown you before. This is the general foundation for what we're doing. Philosophically, we're comparing our data to our model by way of covariance matrices. And this is what we've been doing for path analysis and for confirmatory factor analysis as well. So we're going to operate under this sort of umbrella philosophy of what we're trying to accomplish. But really, how do we? I've been keeping you in the dark. How do these star values, how do these betas and factor loadings and all this stuff get estimated? Okay, so we're going to start in with it here. Based on the start values, first of all, we can plug in numbers that the computer will generate for us. So that star there is 0.83 by a start value. Now, what was that star? If we go back to the model, that was a star based on our beta matrix, which is our matrix of DVs and DVs. Where's my model? There it is. Okay. So relationships, betas between dependent variables and other dependent variables. So that star there was the star connecting ski trip satisfaction F2 with V4 food satisfaction. So that was a 0.83 start value that the computer generated. And the computer is going to continue to do that for the star values in the model. So there's that 0.83. We've got some stars here in our gamma matrix to represent our IV-DV relationships, right? Those ended up as 0.80, 0.89, 3.39, 0.51. Again, these are non-zero. Why it's 0.39 and not 0.41? Well, we're just kind of, we could do that. We could instruct the R program to do that, to use 0.41 instead of 0.39, let's say. But it really wouldn't matter too much in the end because, again, the solution is going to get processed and redone through the iteration process. Here are our variances. This is our phi matrix, so we had a bunch of stars in there that get translated over, and these variances are going to be dependent on the scales of the variables initially. So that 10.68 stands out. That's because that value is a variance for E2. Looking back at the model here, E2 is an error term corresponding to total number of days skied, which is like a number of days variable, which is on a different scale, and presumably a larger variance there, right? The total number of days skied number is going to be larger for these people, and so that's why the computer sensed that in its start value choice, and it became something greater. As soon as I get back to it here, I think it was 10.68? Yeah, 10.68. Okay. So if you were, again, doing this manually, you could do that. You could change that value. Suppose you forgot that scale was different and just put in a 0.5 in there. The computer would be like, come on, Otten, make a better start value choice. And it would iterate longer, but it would ultimately arrive at a similar solution. So anyway, the computer is saving a little time there in the iteration process, I suppose, although it happens so fast anyway, you won't even notice. Okay, so I'm saying stemming from this relationship here that we have looked at in the past, we have an equation, then a matrix equation that you're going to marvel at here in a minute, that's going to get us our model's estimated covariance matrix. So we've looked at how covariances are just unstandardized versions of correlations. So to convert a correlation to a covariance, you see the formula there. So we have a bunch of betas, which are standardized, that we are now, we have start values for those betas, right? And so we're trying to convert a bunch of standardized stuff to covariances ultimately. We're going to get a covariance matrix out of this. So then we're trying to multiply those betas by something that will then serve as, in this case, our standard deviation. We're going to multiply those betas by something to then get unstandardized versions of those betas, but it's not that straightforward because there's a lot of elements that we're working with here. So this is your matrix formula for getting your model or estimated covariance matrix, and it's for the dependent variables. So let's look at this a little bit. Now, the first time, this is that moment for me where I saw this equation for the first time, and I was like, I don't know what all this stuff is, so forget it. I'm just going to move on. So I urge you not to forget it right away. I'm going to give you a couple of tips to kind of break the ice here, break through what's listed, and how to think about this. But ultimately, I think for me now, having seen this a million times, for me it's sort of like seeing a formula for a correlation or a beta or a slope value in a regression, where you look at that equation, you're like, it's really hard to see the connection between what it is in the equation and what the nice, easy interpretation is coming out the other side, for example, for a correlation, right? So then if you stare at that formula long enough, it may help you, it may not. Same thing with this one. It may help you, it may not, to stare at this for longer. But generally speaking, I told you it stems from this sort of conversion from a standardized world to an unstandardized world. So we're taking our betas, the beta matrix in there with the hat on it. That's a beta matrix from your estimated model, and the start values that we just plugged in. You see the phi matrix in the middle, and the gamma matrices are in there as well. These are all your familiar matrices from the Bentler-Weeks model, rearranged, multiplied together, and also multiplied together while the start values are in there. So you've got the beta matrix on either side. It's a subtracted beta matrix, where that I matrix is an identity matrix. What is an identity matrix, you ask? It is one where it's like ones down the diagonal and zeros everywhere else. So we're basically doing 1 minus beta, but in matrix form. So that's a 1 minus beta there. Each time you see that 1 minus beta, it's inversed, and there's a -1 in the exponent there. So that's sort of the equivalent of dividing in matrix form. So you're dividing by 1 minus beta in that sense, and you're also including it in there twice, so you're kind of like dividing by 1 minus beta squared. So that's kind of like the bottom part of the equation if we're thinking about this in non-matrix form. Matrix form, it's the inverse part of the equation. And then you've got these G matrices out on the side. The G is a selection matrix full of ones and zeros designed to pull out the measured variables. So that's just sort of like you're taking some of the betas, but not all, is my quick summary of what's going on there. So you're taking some of the betas, and then you're squaring them, and then you're taking the inverse of them. So anyway, that's generally what's happening there. And then what are you doing with the rest of it? Well, that middle part is a multiplication, and you see gamma in there twice, so you're essentially squaring the gamma matrix. It's gamma, and then there's an inverse gamma, that apostrophe there next to the second gamma hat is a transpose, so you're essentially multiplying a matrix by its transpose. Transposing a matrix means you're taking the rows and turning them into columns, or vice versa. Again, a matrix version of squaring. So if you're thinking about this in non-matrix terms, you've got a squared gamma on the top, and you're multiplying that by this phi matrix, which is your IV covariances. So you've got a bunch of betas in the gamma matrix that you're squaring and multiplying by a bunch of covariances. Then on the bottom, you are taking one, like let's say in the inverse, but it's sort of like the bottom of the equation. You're taking 1 minus the other betas and squaring those. So it's kind of like taking your covariance matrix of IVs, multiplying it by some betas squared, and then dividing by some other betas squared. And it's like a really fancy or complicated version of our covariance matrix, our covariance equation, because you've got correlations multiplied by standard deviations of one by the standard deviations of the other. So, but it's not a direct application. I said it's stemming from that equation. Still, even with some of the words that I just put into my explanation here, you're probably wondering a little bit how all this stuff came to be, and that's fine to wonder that. Like I said, if you want to follow up with me, we can look at more literature on this and try to narrow down a little bit better why this is all resulting in a covariance matrix for your DVs that's estimated or that's representing your model, your hypothesized model. So that's the big equation. Then we've got a couple others to show you. This is the result. We've got a covariance matrix of the DVs. There's 4 DVs in this case, and so you've got covariances estimated for each one there. And we can stop, if you wanted to pause me there, we could talk more about what this looks like sometime in the office as far as which variables these are and what these, why these values might have come out larger or smaller. But meanwhile, these are all still based on the start values that I covered earlier. These are the other somewhat smaller versions of that big one. This is the estimated covariance matrix for the IVs and DVs. So we're breaking it down. What we just did was DV with DV. Now we're doing IV with DV. And these are actually all going to add into one matrix in the end. So like you take this DV covariance matrix, this is going to be one section of your overall covariance matrix. The next section is going to be this one. This one I can offer another explanation. It may or may not be useful. We've got these selection matrices out here on the side, again selecting out certain betas, and in this case also certain elements of the phi matrix as well. You've also got a gamma in there. Why the gamma is not squared, I'm not exactly sure, but it's because we have IVs and DVs in here ultimately. So maybe since that is what the gamma matrix is, a bunch of relationships between IVs and DVs, maybe that's why we don't square it. I don't know. We can look into it further. But anyway, this is going to give you just, in this case, a short 1 column by 4 row matrix here to represent your IV-DV relationships and their covariances. This is your covariance matrix for the IVs, which is actually just there, since there's one IV in this model, you're just getting a 1 out of it. So this is a little bit clearer maybe in its origin when you see just that 1 was the number that came out of it, because you're just, with the G matrices here, you're just selecting out a 1 from the phi matrix. And that was the one for F1, which was our predictor in this model, which we had set to 1 originally as our variance. So that is when we're setting a variance to 1 for F1, that is our start value. And so all we're doing here is pulling that 1 out of the phi matrix and including it in our ultimate covariance matrix as well. Okay, so here's the result. You can refer back to the previous slides to see where this all came from, but basically the DV-DV covariance matrix in this case is like the top left, so it's the first 4 rows and the first 4 columns of this matrix. The DV-IV matrix was the 00.39.33. You see that on the far right column, and then you see it in transposed form on the bottom row, and then that 1 that came out of the other matrix, which was just the variance for F1, that's in the lower right-hand corner. So there's an arrangement here. You just have to keep this straight in the end as far as like which rows and which columns are represented. But ultimately this is going to match your data covariance matrix, so you just have to make sure your data covariance matrix is formatted in the same order. Really what the computer program is going to do for you is just once you enter in your variables, it's going to keep all that straight for you. So it's going to actually generate a matrix, and you've already seen it do this actually, generate this matrix and then compare it to the actual data covariance matrix. But wait, we can't compare yet. Why not? Well, this was the matrix that was generated based on our start values, so this is a valid estimate of the covariance matrix. But now we need to iterate that solution. So we need to bring it as close as possible to the actual covariance matrix to give our model the best chance it has, or to sort of maximize our chances of making it, having it represent our data. And so I just kind of foreshadowed a little bit by calling it maximizing. We're going to use maximum likelihood here to do that, to match up our model to our data. And then once we do that, we're going to subtract, or the computer will do this. The computer does all of this, but what the computer will do, and we can try to follow along with, is watch as it subtracts each corresponding value, one from your hypothesized model covariance matrix and the other from your data covariance matrix. And it's also going to measure that distance. So that's a distance, right? That's if two elements in the top left, let's say, of these covariance matrices are way far apart from each other, that's a far distance. It's a suggestion that our model is not good for that particular covariance. But we hope that in general, those distances are small. Okay, so what does this look like? Another formula, another opportunity for you guys to go, oh my God, I don't know what any of this is. Well, actually, this is slightly simpler, I want to say. This is sort of, we've got our covariance matrices now. One of them, so the notation here is it might throw you off. There's some Greek letters that maybe you haven't seen before. There's this theta thing, which is, this is overly complicated in notation, in my humble opinion, but I don't know. People have come up with these things for reasons. So anyway, the actual covariance matrix is S in this case, and the estimated or model covariance matrix is the sigma. And so when I say we're subtracting elements of each one in place, so like the top left of the real data minus the top left of the estimated model data, that's a subtraction for that element. And then when you subtract in matrix form, you're subtracting basically an S from a Greek letter, or a Greek letter from an S, I guess in this case. And we're doing that, we're taking the transpose and then we're multiplying it by itself on the other end there. So that's a sort of like taking it and squaring it. And that's essentially what we're doing with chi-square, right? We're taking observed minus expected and squaring it. This is just that in matrix form with a mysterious W in the middle. So again, observed in this case could be your data, which is the S. Expected could be the model covariance, which is the sigma. And so if you're doing observed minus expected and squaring it in matrix form, you're doing the first matrix transpose multiplied by the second matrix, or the subtracted matrix transpose multiplied by itself. So then in the missing element there is the W matrix. So this W matrix has been debated by SEM researchers a lot. It is the main, and really, like, you know, if you get to the point where you're curious about the W matrix, you kind of generally understand what it's doing, and then you start delving into the different options for a W matrix, then you've made it as far as I have, because I haven't really made it past that point, nor have I needed to really in my studies. But what is this matrix? Okay, it's a weight matrix. Basically, you're weighing the differences, and these are squared differences, like I mentioned, between data and model covariances. So you're weighing these different subtracted values differently depending on what's going to make your model look like the data, or what's going to make the data look like your model. And so then I mentioned this has been debated a lot over the years, the choice of this W matrix. And so maximum likelihood is the choice typically. And so what we're doing here is we're choosing a matrix W that allows us to, again, make our data look as close as it can, make our model look as close as it can to the data. So we're multiplying some elements of the matrix differently than others. We're not just, let's say, suppose we didn't have a W matrix, we would just be like, okay, let's just square the differences between our data and our model, right? Let's take each element of the matrix, subtract them, square them, and call that our difference. That's basically the foundation for our chi-square test, right? When we're doing our chi-square test, we're basically doing that. But then we've got this W matrix. The W matrix will say, hey, look, like the relations, the factor loadings here, those are not important. Those are going to be strong no matter what. Really, we got to see if the relationship between, let's say, V5 sensation seeking and the DV F2, let's try to make that one as close as we can to what the actual data is telling us. And so we're going to weigh that one really heavily, and we're not going to care as much about the factor loadings because Well, there is no because. In this case, it's just a formula. What maximum likelihood does is it basically just uses the inverse, or the inverse of the estimated covariance matrix that you've already generated in place of that W. And so you're basically just kind of dividing by this matrix. And so there is no decision making involved. Why I was talking about it as if it was a decision, because, well, you can do this and then you can change and you can switch and not do maximum likelihood. You could also do instead one of these other methods that we're not going to talk about too much in this class, but these also exist and might call for, instead of, let's say, weighing that V5 F2 relationship really strongly, maybe we're going to weigh the factor loadings more strongly. Or maybe there's some other method to the madness where it's not based on whether it's a factor loading or not, it's based on some other criteria. Maybe if it's a big difference, we're going to weigh that one less, and we're going to weigh the small differences more, and we're going to see how that works. So those are some hints as to what the choice of the W matrix will do. Again, it's a subtracted, it's a matrix of subtracted values, right? That S minus sigma, that's your actual data, elements of your covariance matrix, and then you're subtracting out the elements of that same covariance matrix as according to the hypothesized model. So you're making that subtraction. You're squaring those values as in you would in a chi-square, let's say. And then your weight matrix, your W matrix there, is weighing certain subtracted and squared values, certain elements of that matrix, more than others, to try to match up your data as closely as it can to the model. So you're just trying to give it, these methods are giving, it's a way of giving yourself a chance to make your model match up to the data, and it's doing it in an objective way by virtue of maximum likelihood, which is most common. You're dividing, or you're taking the inverse of the model estimated covariance matrix and using that for W. That's objective, right? These are other objective ways. A non-objective way would be to go in there and weigh things as you choose, but then that's not anymore a mathematical transformation of that matrix, and so then you're cheating, essentially. So you gotta rely on some transformation that's a mathematical kind of you're taking that matrix and you're doing something to it and making it a different version of itself. And if you studied exploratory factor analysis, you're kind of doing this when you're extracting factors and rotating matrices. You're doing a similar kind of iterative process, and maximum likelihood was useful there as well.
Okay, so there's one other series of estimation methods to mention here, and that is the RGLS and RLS methods, which are being developed even as we speak. As of this filming of this video, these are not available in R, the computer program, at least not directly. You have to do something with maximum likelihood and then do a fancy calculation on top of it to get these methods of estimation. So don't worry, I'm not assigning you these yet. However, the claim is that these methods get you your fit statistics in small samples more accurately than if you have maximum likelihood or one of the others that we just mentioned. So there is good performance from these estimation methods in small samples, and then they actually do fine in larger samples too. So why do we not use these? Well, maybe we will in the future, but meanwhile, let's go with what the experts recommend for now.
So we will go ahead and use maximum likelihood. It's cited as the most frequently used estimation method in SEM. Sometimes these other methods come into play more when you have weird-looking data, basically non-normal data. But you can read up on when some of those other methods might be more popular. Meanwhile, we'll go with maximum likelihood. Generally, so maximum likelihood is not specific to SEM. Like I mentioned, it's used in exploratory factor analysis and other times in the world of stats. It's a way of taking your data and matching it up to a hypothesis, in this case, trying to maximize the likelihood of your data given your model and vice versa. Okay, so we chose maximum likelihood. What did we say? So let's use maximum likelihood to guide our choice of the weight matrix, which will then minimize Q. What was Q? Let me go back and look at Q. So many letters. Q was the transformed matrix here that is the transformed version of the S minus sigma. That's your differences between data and model covariance matrices. Okay. You guys tired yet? You can pause me. We'll get to the end here in a second. All right. So here's what the final estimated covariance matrix looks like. It looks like a little bit different than what we had based on our start values. So you can go back and forth between the start value version and the covariance matrix that we have here to see what the effect was of doing that iterative process using maximum likelihood, choosing W, all of those things. Sometimes when I look at this and I compare it back to the start value matrix, I'm like, well, nothing much happened. All that effort for nothing. But since the computer is doing this, you're not really exerting much effort. So I guess that's it's all the same. But anyway, this is our final estimated covariance matrix. We're now giving ourselves the best chance we have of getting this as close as possible collectively, all these covariances, to our actual covariance matrix, which is here. And so then you can go ahead and start your subtracting. You can start with the top left. Let's say there's a 1 there for the top left of this matrix. There's a 1 there for the top left of the other matrix. Okay, we're at 0. This is an exact match. Okay, let's go to row 2. Row 2, the first element there is 0.70 in our estimated matrix. And in our actual matrix, 0.70. Okay, it's exact. Okay, our data is doing really well. Let's go to the third element of that first column there in the third row, 0.63 in our data. 0.63, oh, 0.51. Okay, we're off by 0.12. Okay, our model is not perfect. So that's the process now. We're just kind of going element by element and comparing matrices. There's a lot, obviously, that goes into the creation of this one. And so that's where all the work exists. But once you've got it, you can make some comparisons. You can do that chi-square test. The chi-square test will now make more sense. You might even be able to do it by hand. I don't know if you want to, but this is our final residual matrix. This is the one where I was doing those subtractions there. You do it for each element of the matrix, and you can see in the top left there's 4 zeros. That means, okay, we're doing a great job for those 4, or the data and model match up perfectly. But actually in the lower left corner there with the 0.30 and 0.21, same as the top right corner, you see there's some differences. So we then evaluate these differences collectively to get our model fit. And this is the observed and expected process that I was referencing earlier. We can do our chi-square test of model fit, which we've covered already, to see how well they match up.